In the example, we're given trapezium TUVW, and we're told that the sides WT, TU, and UV all have the same length, and angles TWV and UVW are equal. And given this information, we're told to prove that. Before going into the proof question, I'll just make a note that from now on, we'll look at various proof type questions, which definitely forms a pretty big component of this topic, and it tests your mathematical knowledge as well as problem solving skills. And it will definitely form a good chunk of the marks in the Euclidean geometry questions in the exam and your tests. So you need to get some practice with proof type questions. That being said, here's the first part of the question. We need to prove that line UW bisects angle W, meaning this complete angle. And bisect means it cuts the angle into half. So with these proof questions, they will generally come in two forms. One form is when they'll give you a word description of what you need to show. And the other situation is where you'll be given a mathematical statement that you need to prove. So in this case, we have the first case where we have a word description. So for those sort of proof questions, the first thing is start by identifying what you need to show mathematically to answer the question. So the question asks us to prove that this line splits this angle into two equal halves. So one way we could prove this is by somehow showing that this angle is equal to this angle. In other words, TWU is equal to UWV. Now with these word description type questions, this step is something you would need to sort of identify yourself by analyzing the situation. And while you can write it as part of the answer, it's not necessary. I would suggest in a test or exam, just write this somewhere on the side, just so you know in your head that that's what you need to do. So we need to show that TWU is equal to UWV. And here's the strategy to use. First thing is, notice that this triangle, meaning the triangle with the angle TWU, has two sides of equal length. Therefore, it's an isosceles triangle. And in an isosceles triangle, the two angles opposite the equal sides are the same, meaning TWU is equal to TUW, since TW is equal to TU. Then let's go back to the diagram. So you know this angle is equal to this angle. Then since this line and this line are parallel, as they normally are for trapezium, so you may not already know this rule by head, that for trapezium the top and bottom sides are parallel, but we will definitely go through this later in the polygon section, after which you will naturally know this. But anyway, since TU and WV are parallel, TUW and UWV would be equal, since they're both alternate angles. And therefore we found a nice path linking TWU to UWV, and we've therefore shown that TWU is equal to UWV. And this proves that the line UW bisects the angle W. And for the next part of the question, if TU to WV is equal to 5 to 6, show that area of triangle TUV is equal to 5 over 11 times area of TUVW. Let's look at the diagram again. So the question said that if the ratio of TU to WV is 5:6, show that area of TUV is equal to 5 over 11 times area of TUVW, meaning area of the entire trapezium. So I'll start by just writing down the information given in the question. So they told us that TU to WV is equal to 5 over 6. In fraction form, that looks like that. And we can relate this to areas by applying the triangle proportionality rules we looked at earlier. Going back to the diagram, the triangles TUV and WUV both have the same height since TU and WV are perpendicular to each other. So both triangles TUV and WUV have the same perpendicular height. And for triangles with the same perpendicular height, the areas are proportional to the bases, which for triangle TUV would be line TU, and for triangle WUV would be line WV. And since they told us in the question that the ratio of TU to WV is 5/6, we can also say that the ratio of the area of triangle TUV to the area of triangle WUV is also 5/6. Oh, and I forgot to mention that to answer the question, we don't need to know how to calculate the area of a trapezium, meaning we don't need to know the specific formula, because I haven't gone over that yet, but I will later on in the polygon section. So that's the first thing. And then the other thing is that, remember that I mentioned that they will give you two types of proof questions. One where they give you some statement and you have to interpret it correctly. And this is the second type where they told you specifically that you need to show that area of TUV is 5/11 times area of TUVW. And in that case, the starting point is usually just note down whatever information they've given you in the question and then see how you can relate that to the terms that are in the statement that you need to prove. So I went about it by writing this 5/6 ratio as a fraction. Then I found a way to relate this to area of TUV since we need to bring it in from somewhere. Cool. Then the next step is I want to see if I can write the area of the trapezium in terms of this area of triangle TUV. So at the moment we have area of TUV over area of triangle WV is 5/6. Then going back to the diagram, we have area of TUV over area of WUV is equal to 5/6. Then relating TUV to the trapezium, we can see that the area of the trapezium would be the area of triangle TUV plus area of triangle TWV. And from the way the diagram is set up, we can tell that triangle TWV has the same area as triangle UWV, since both triangles have this base of WV and the same perpendicular height. So we can say that triangle WUV and triangle TWV are equivalent. And since they're equivalent, they would have the same area. So I'll replace the denominator term of area WV with area of TWV. Cool. Then remember I just said that we could represent the area of the trapezium as the sum of triangles TUV and triangles TWV, meaning this triangle and this triangle. Then what I'll do is replace this denominator term of area TWV with area of TUVW, which should be the same as area of TUV over area of TUV plus area of TWV. And since we have numbers already for area TUV and area TWV from over here, meaning 5 and 6, you can substitute these here into this fraction to give 5/5 plus 6. Therefore, area of TUV over area of TUVW is equal to 5/11. Then we're pretty much done. All you need to do is cross multiply this denominator with a fraction of 5/11, giving area of TUV is equal to 5/11 times area of TUVW. And that was a mathematical statement given in the question that we had to prove. This one. And since we've proven it, you can just conclude the question by saying, hence shown. And that concludes this example. Then let's move on to something known as the proportion theorem. Okay, so this part is mainly going to be a proof, and a pretty tricky proof, so it may be a bit heavy. So I'll just suggest, if you've sort of been marathoning the video so far, maybe just take a breather for a few minutes and then come back to this with a fresh mind, because yeah, a lot is about to happen. That being said, here's the proportion theorem. The proportion theorem states that a line drawn parallel to one side of a triangle divides the other two sides proportionally. So you should know the statement by head and memorize it and understand what it means and what it implies. And unfortunately, you also need to know the proof, because in the exam they could ask you to prove it. I'll just say it's definitely not impossible. It's just a little bit tricky at first, but I'll do my best to go through it so you can get a good grasp of what's happening. So here goes. So we'll start off with a basic triangle ABC. Then the theorem says that a line drawn parallel to one side of a triangle divides the other two sides proportionally. So what I'm going to do is I'll draw a line parallel to the side BC, and I'll call the line DE, which will look like, cool. So I've drawn a line parallel to this third side, and I need to show that line DE splits the other two sides, meaning lines AB and AC, in the same proportion. I'll tell you how I prove that exact statement in just a second, and to do this I need to add in 4 extra lines. The first 2 of these are by joining D to C and B to E, and the other 2 are by drawing a line perpendicular to line AD and connecting to point E, and another perpendicular to line AE and connecting to point D, which will look like, so that's the line joining DC, and that's the line joining E to B, and this is the line perpendicular to AD and connecting at E, which I've named as H1, and this is the line perpendicular to AE and connecting to D, which I've named as H2. And how I'll prove that the line DE, which is parallel to this third side BC, divides the other two sides AB and AC in the same proportion will be by showing that the ratio AD over DB is equal to the ratio AE over EC. So the first step is find the ratio of the area of triangle ADE over the area of triangle BED. And to show you clearly how we'll actually get values for the two areas, I'll need to turn this diagram around a bit. And this is how it looks like. So, of course, the area of both these would be half of base times height. Then we need to replace each of these with actual lines in the diagram. So for triangle ADE, the base would be the side AD, and the height, meaning the perpendicular height, would be this height H1. Then for triangle BED, meaning this triangle, the base would be the side BD, and then the height, meaning the perpendicular height, would also be H1. Since this line AB is parallel to the line upon which the top vertex point lies, meaning this blue line is part of the paper. So area of triangle BED is half times BD times perpendicular height H1. And the halves would cancel off and the H1s would cancel off, finally giving the ratio as AD over DB. Cool. So we've got the first part. Then for the next part, I'll need to go rotate this diagram again so that this time AC is the part at the bottom. Like that. So we'll determine the ratio of the area of triangle ADE divided by the area of the triangle CDE. And as usual, both the areas would be half base times height. Then we just need to substitute these with lines from the actual diagram. So for triangle ADE, this time we can calculate its area by saying half times base AE times height H2. Then for triangle CDE, we can determine the area by saying half times the base of CE times the height, meaning perpendicular height, H2, since this line and the line upon which the point D falls are parallel to each other. Therefore, h2 is a perpendicular height, and area for CDE is determined by saying half times base CE times height h2. CE or EC, same thing pretty much. And then both the halves would cancel off and the h2s will cancel off, leaving just AE over EC. Then for the next step, I'll need to use the same diagram but in its original orientation where A was at the very top. There we go. And looking at this diagram, since as defined at the beginning, we drew the line DE to be parallel to the line BC, we know they're parallel. And from this, we can say that the area of triangle BED would be equal to the area of triangle CDE, since both would have the same base of DE and have the same perpendicular height. So this triangle and this triangle, both base DE and perpendicular height like this. So since the area of BED is equal to the area of CDE, we can play around a bit with the previous ratios we determined for the various areas. And just as a reminder, when we first flipped around the diagram, we had got the ratio of the area for ADE over the area of BED. Then when we flipped it around again, we got the ratio for ADE over CDE. Then, by returning it to its original orientation, we established that area of BED and area of CDE are equivalent here. Therefore, since these two fractions have the same numerator, and we deduce that the denominators are also equal, we can therefore equate the two fractions to each other, like shown here. So the fraction of area of ADE over area of BED would be equal to area of ADE over area of CDE. And we can therefore equate the simplified fractions as well, giving AD over DB is equal to AE over EC. In other words, this over this is equal to this over this. And that proves that drawing a line parallel to the third side will divide the other two sides in the same proportion. And that's how you prove the proportion theorem. So it seems a little bit complicated, but just do it and keep repeating it a bunch of times and it'll stay in your memory. Then you may remember I mentioned earlier in the revision section that with these various theorems, you should have a full rounded understanding of them, meaning you should be able to interpret them from the reverse end as well. And these are known as converse theorems. So the converse for the proportion theorem is the converse proportion theorem, naturally. And what it says is that if a line divides two sides of a triangle in the same proportion, then that must mean it's parallel to the third side. And the reason you need to know these converse versions of them is because sometimes in certain questions they could, for example, give you a circle with some triangles and stuff in it, and then you have one line cutting the triangle in the middle, and then in the question they'll just tell you that this line divides the two sides equally. But then they won't tell you that it's parallel to the third side. So then you need to use your knowledge of the converse proportion theorem to deduce that, okay, yes, this does imply that the third side is parallel, and then you just apply this to determine various angles and things such as corresponding angles and alternate angles based on this fact. So I'd suggest once you've memorized the normal proportion theorem and kind of understand how the proof works, just try to memorize the converse proportion theorem as well, just so you have a full rounded view of the rule. Then the last bit of knowledge you need to learn related to proportionality is a special case of the proportion theorem, and this is the midpoint theorem, which you've definitely seen before and I covered in the revision section already. The midpoint theorem says that the line joining the midpoints of two sides of a triangle is parallel to the third side and half its length. such as shown in the following triangle, where the point F is the midpoint of line EH and point G is midpoint of line EI, and according to the midpoint theorem, the line joining these two midpoints would be parallel to the third side HI and half its length. So writing this down, the midpoint theorem says that if EF is equal to FH and EG is equal to GI, then FG is parallel to HI and FG is equal to half HI. So it's not really any new information, it's pretty much the exact same midpoint theorem from before. But I think the new thing is you just need to know in your head that it's a special case of the proportion theorem. And that's pretty much it. Then as I had mentioned, for just the general proportion theorem, you should just be able to recognize the converse of the midpoint theorem as well, which is a line drawn from the midpoint of one side of a triangle and parallel to the other side will bisect the third side of the triangle. So it's just the same as the midpoint theorem, just sort of looking at it from another direction. Then I'll just conclude this section with going through two examples covering the proportion theorem as well as the midpoint theorem before moving on to the next section, which is polygons. Here's the first example. In the diagram shown below, PQ is parallel to TR, and the lengths are as indicated in the diagram. So side QR has a length of 4 units, line RS has a length of 12 units, line TS has a length of 18 units, and line PT has a length of alpha. Then the question asks us to determine alpha. So we'll apply the proportion theorem to this, meaning that since we know that RT and PQ are parallel, that means RT splits the line PS and the line QS in the same ratio. Therefore, we can say that 4 over 12 would be equal to alpha over 18. Then just simply rearrange for alpha and you get it as 6. Then here's the second example. In triangle ABC, DE is parallel to AC and side AD is equal to 16 units, side DB is equal to alpha, side BC, being this whole side, is equal to beta, and side EC is equal to 21. And we can also tell that side BE is equal to beta over 3. So given all this information, what are the values of alpha and beta? We've been given quite some information related to beta, so I'll determine beta first. So what we know is that side BC is equal to beta and side BE is equal to beta over 3. Therefore, side EC, for which we actually have a value, would be equal to BC minus BE, or in other words, beta minus beta over 3, which would just be 2 over 3 beta, which is equal to 21. Then you just simply divide 21 by 2 over 3, and that gives beta as 31,5. So we have a value for beta, and to solve for alpha, we would use the fact that sides BC and BA will be divided in the same proportion by line DE. And since we know the total of this side is beta and this portion is beta over 3, that means the ratio of this portion over the total portion is 1 over 3. So applying that to this side tells us that alpha over alpha plus 16 is equal to 1 over 3. Then you cross multiply to give 3 alpha is equal to alpha plus 16. Then just rearranging for alpha and dividing gives alpha as 8. And that concludes the ratios and proportionality section of Euclidean geometry. Next, we'll look at polygons.